higher tension as you're at an angle. Okay. By the way, if you go through this derivation, you come up with an expression for the tension as well. All right, that's circular motion. All right, now I've got this apparatus. We may talk more about this. We don't really have the tools yet to describe this system mathematically, because this is actually a little more complicated than you may think it is. Okay, this motion. You think it'd be easy, but it's not. Okay, I got it attached to a string. Now I showed you circular motion. This is oscillatory motion. You see the difference? This thing isn't going in a circle, it's going back and forth. Okay. Now, like I said, we don't quite have the tools yet for describing the system, but you might think about this while we're on this. Let's talk about this for a minute. If I've got it dangling like that, what is, and this is a point of review, what is the tension on this string here? The weight of the bob, which is what times what? mg. mg, well, ma in general, but now we're talking about gravitational acceleration, so it's mg. So that's mg. So the tension on this string is mg. Okay? I mean, that's pretty straightforward, right? We should all work with this easy. If I do this, do you think that affects the tension on the string? Why? Because this motion gives rise to a radial acceleration. Okay, remember, radial acceleration is going in this direction. Okay. So you got a little bit of radial. Now the radial acceleration is not constant in this case. All right. Also, you have a tangential component because the tangential acceleration is not constant either. Okay. Now, if I do it just a little bit like this, I've got a little extra tension on the string. If I bring it all the way up here, let's hope this doesn't fly off. Okay. What about the tension on the string now? Probably a little more, right? So the wider that amplitude of oscillation, probably the greater the tension on the string. All right. Now when I'm holding it up here, and by the way, the tension on the string is not constant either. If I'm holding it up here, but if I'm not pulling on it like this, if I'm just holding it, the tension on the string is essentially zero. There's no tension on the string. When I let it go, now there's tension on the string, and that tension is going to vary depending upon what that angle is. And of course, that angle is constantly varying because of the oscillatory motion. Okay? That's why I say this situation is a little bit more complicated to analyze than the other one. All right? But it's good to kind of know some features about this because, well, it makes for a good test question. Okay? So you can talk about things, about what's happening to the system without going through the mathematics. I think all of you would agree with that. If you want to quantify it, you got to do the math. So if you really want to put numbers to all this, then this is when you have to invoke your mathematical formulation. Okay. So I want to illustrate there's a difference between oscillatory motion and circular motion. Okay. And oddly enough, the circular one is a little easier to analyze. And that's the one I have on the board. Okay. So the one on the board is this one here. Okay? So we're going to say that the angular speed, omega, is constant. And, of course, the higher the angular speed, the higher the angle theta. Okay? What I want you to do is derive an expression that relates theta to omega. So what you're going to do the free body diagram, and you're going to have an x component and basically a y component. Yeah, and I think the x and y component should be like a perpendicular parallel to the horizontal. Remember, the circular motion is going to be horizontal. It's not going to be at an angle. Put it at an angle, that complicates the mathematics, okay? So it's horizontal, okay? So you got horizontal, and then you got a vertical, all right? So we set up our coordinate system, do it this way. X will be y, x will be parallel with horizontal. So draw the free body diagram for Bob. Do the x, the summation of forces in the x direction, the summation of forces in the y direction. One of these is 0, the other one is not 0. Okay? All right. Give you a couple minutes to work that. By the way, if you want to get with a classmate, and just make sure you keep your mask on, get your classmate if you want to kind of put your heads together, see if you can figure this out.
And that's tension, that's, what, I don't know what this is. Is it said, wasn't that tension too, like, tension cosine theta? Yeah, that's tension.
Yeah, I just didn't want to have it on.
I think,
But what is this? What's this one?
was it not tension sine theta?
I said this would be T, like the other one's trying. So it's like this.
So I think,
MG going down.
Yeah, that's
T
what I
sine
have.
theta, T cosine theta.
I think the y is gonna be equal, like, the sum of the forces in the y, I think that's the one that's gonna equal 0. Like he
By the
said,
way,
one of those is gonna
the
equal
radius
0.
of the circular motion, you can call it R,
Oh,
but obviously you're going to have to replace it with L times some trig function. Right?
oh, so it
It's L
would be,
sine theta, right?
Oh, so it's not T.
so it'd be L instead of T.
So
What does L mean?
length.
Length?
So this is L sine theta. This is L cosine theta.
That's what I'm thinking. But I don't know about that bottom one, because it's R. Maybe that's
He
what,
said we would replace it.
maybe that's what
with
R is
the-
equal to.
Yeah, he said we'd replace it with the function.
By the way, the final equation is actually fairly simple. Getting there might not be so simple.
I'm thinking the Y.
Why do you think it's the Y?
Because it's just hanging down. Like, you can still do your L cosine theta plus mg equals 0.
Oh.
Like, that's what I'm
But what is
thinking.
then, what is the X equal?
The x would be
L sine
L
theta?
sine theta just as much as the gap. Oh, it may be going one way or the other. Yeah. Because it
I
has
would like this way.
yeah.
Like this.
And that may have to do something with that radial acceleration.
Yeah.
Something, I don't know. It's all they got. Not of ideas. I think I'm just annoying. I hate erasing stuff. So could you put like 10 with that one? Like if we had to? Like opposite over. No, that's never mind.
Opposite or different?
But that's
Different.
actually yeah, that's actually like opposite
That's the
over
hypotenuse.
yeah.
We've got the free body diagram. I've labeled everything. Actually, that was the T cosine. So the X component because theta, because these two lines are parallel, that means the same here as theta as well.
What's the one going up?
The other one.
Like the one going
the
up?
same one?
Like
They
the one
both-
going at an angle?
Like, you see the MG, but goes straight up from
I
it.
think we'll go fit. I think it's because something like
Oh, okay. Yeah. I guess it was the one having an extra one.
what extra?
Like the arrow going up.
Right, before you counted that.
It's kind of do equivalent of normal force, but for the thing in motion.
Yeah. That bar is straight. Where you got that?
I don't know any. I think you can see the force.
So I see what you're doing. Okay. You got, yes, it was good. You got another
Okay, so I just labeled,
it's R.
yeah, what you
It's R.
have. That's all I did.
R is a link. Okay. So it has to be related back to L. Not to separate out force terms from your geometry. See what you're doing here. Really good. This would be. Oh, sorry. Yeah, no, this should be, oh, sorry. I see now. No, I how about that? Any progress? Okay, all right, so here's our free body diagram. Okay, let's look at these terms here. Okay, the x direction, that's the same plane that your circular motion is in, and circular motion is basically a second law problem. That force sums up to be the mass times the radial acceleration. The question is, what do we have what force do we have in the x direction? We basically got one. That's this one right here. That's the one we have in the x direction. And what's that equal to? Okay, this one would be T sine theta. So, the sum of the forces in the x direction, T sine theta. Okay. But because that's the plane, the same plane where the circular motion is in, that's going to be equal to m times the radial acceleration. Radial acceleration equals m where r is this distance, which is basically L sine theta. Okay, so that's our equation in the x direction. Now in the y direction, because there's, if you look at the motion, you gotta think about this. Is there any movement in the y direction? It's this direction. Is there any movement in the y direction? No, there's not. This is only in the x. What that means, because there's no movement in the y direction, guess what? This summation is equal to 0. But we have two forces in the y direction both of which, of course, cancel each other out. That would be this one, you could say is negative because it's going down, and this one here, which is positive. Now, what is this one? In terms of the tension, this is what? Okay, so this is equal to T cosine theta. All right, and then this one is just minus mg is 0. Okay, there are your, now we haven't done anything with r. R is equal to L sine theta. So we can take this term, plug it back in here. So what you can do is solve for the tension, and replace that term for t here, and then that will give you theta in terms of the acceleration g, and also in terms of L. And the masses will cancel. Okay, so now at this point it's an algebra problem.
I have a question.
Yes, ma'am.
How did we get R as L sine theta when it's the same as T sine theta on most everybody got?
Okay. It's a good question. When you got, this is basically, this is two things. This is a force vector
Okay.
pointing in this direction. It has the magnitude T sine theta. But it also is a geometric parameter, R.